So we're going to start talking about how compounds form into larger structures. So we're going to be talking about bonding, but we're also going to be talking about forming larger structures. And I'm going to start with ionic solids. Ionic solids are, in a sense, the easiest thing to think about. You have something that has lost an electron, like sodium plus, right? And the energy needed to remove that electron is known as the first ionization energy, which you know. And you're also going to have Cl minus, in a crystal, let's say. And that's, well, how did Cl go from a single chlorine atom to Cl minus? Well, that energy is the electron affinity. So you can see how we're going to be building on what we've been discussing. And when we've written about these in solution, they're separate, right? And of course, they're not really separate. They're crowded around by the water molecules. But here I want to talk about what they look like in a solid. You also know that Na plus should be much smaller than Cl minus, because every time an element or an atom loses an electron, it becomes a cation. That's cation, not cation. A cation or cation is smaller than the starting atom, whereas an anion is larger. A negative ion is always larger for reasons we discussed in the previous chapter. So here's an example of how the crystal might look. This is a depiction of sodium chloride in a crystal, and it forms a simple cube. I should point out that lots of different types of crystals can form. This is known when it arranges like this as a crystal lattice. And there's an energy associated with those bonds forming because each of these are either positive or negative. And notice that the sodium ion is smaller than the chloride ion. And they arrange in a cube. There are tons of other ways that they can go together to form a rhombus or a diamond shape, all kinds of things. But for now, we're just stick with the simple one. So the first thing we want to know is, how do we predict how strong this energy is? Now, of course, breaking apart this structure will require you to break interactions between the sodium plus and the chloride minus, and that has to require input energy. Now, there might be a trade-off because of the atoms being able, or the ions being able to move more freely. We've discussed how entropy plays a role. But also, the major deal is there's a trade-off in terms of the bonds between the ions and the water itself. And we're going to spend a bit more time on this, but we've already talked a little bit about water being a polar molecule, a molecule that has one side partially charged and the other side charged the other way. So, for example, you can see that on a water molecule, the oxygen side has a partial negative charge and the hydrogen side has a partial positive charge. And when you hydrate or dissolve a solid like a sodium chloride crystal, what you're actually doing is replacing the bonds among the ions with bonds to the water. Now, they're weak bonds, but there's a lot of them, and so there's an offset there. So there's always new bonds forming with when it dissolves. So how are we going to determine whether or not something will be soluble? And it really comes down to whether the bonds that are possible with the water are enough to offset breaking the bonds of the crystal. And we have a simple equation for that. That's based on something called Coulomb's law. And the actual form of it is the force that's attracting the ions to each other is equal to some constant, and we're not going to worry about that. It's going to be different for different compounds and different shapes, and we're actually going to end up leaving it off. Some constant times the important bit, which is the product of the two charges, Q1 times Q2, divided by the radius squared, the distance between the ions squared. So how do you use this? Well, like I said, we're not really going to use the constant. We're just going to compare different structures and say, well, in the case of sodium, sodium has a +1, chloride has a -1, so the product of that is just -1. And then it's going to be divided by the radius squared. And we're not actually going to use the radius too often. Occasionally, we'll actually have it available. But this is the half the distance between the two. So the distance between the molecules, or the ions, I'm sorry. And that has to do with how big the ions are. And so you already have the tools to assess which ions will be bigger. So for example, if you look at the periodic table, you know that chloride is going to be bigger than fluoride because fluoride is up here on the periodic table and chloride's down here right below it. And as you go down the table, you get larger. Similar, you know that lithium will be smaller than sodium, right? And then you look at things like magnesium 2 plus, right? It's going to get even smaller. So we'll be able to compare two different compounds, two different crystals, and just make a prediction based on what's the product of the charges, and then how big are the ions. And you want to look at the charges first. They're going to have the biggest effect on it because the radius is going to be very small and the differences will be very small. So really you want to look at the charges first, and then if the charges are the same, you're going to look at the relative size of the things. Here's the most important thing. All right, listen up. You don't look at the sum total of, say, all the positives. So for example, if I'm looking at Na2SO4, because SO4 carries a 2 minus overall, and sodium is a 1 plus, when you look at the Coulomb's law for this, you only count one sodium at a time. So you're interested in the force attracting each sodium to the SO4 2 minus. Yes, there's another one over here, but it has no net gain effect on the interaction over here. So you're interested only in the interactions between each individual ion. So it's the charge on the ion. Let's take a look at a couple of examples. Well, let's do that one. Na2SO4. So what's the product of Q1 times Q2? Q1, sodium, is plus 1, or 1 plus, and we're going to multiply that by 2 minus, because this will break into 2 Na pluses. We'll actually draw them separate, just so that you don't get tempted to think of them as the same thing, right? 2 individual sodium pluses stuck to an individual sulfate. And so looking at this, the charges are going to be 2 minus, right? 1 plus times 2 minus is 2 minus. What about comparing it to magnesium sulfate? Well, magnesium sulfate carries a 2 plus, so Q1 is equal to 2 plus, and Q2 is equal to, change to subscript, and Q2 is equal to 2 minus, so the product of those charges is 4 minus, right? And then, magnesium is actually fairly small because it's a 2 plus. And so magnesium sulfate is, in fact, very soluble. You may remember that sulfates are almost always soluble, and that really has to do with how big it is, because what you've got, and we'll look at how to draw this better later in the year. Looks something like that. Well, it's really large, and so the distances are quite large, and so that keeps it from being as strong an attraction. Nitrates, NO3s, are also tend to be very soluble. But let's look at some other cases. How about magnesium oxide? Charges are right. O makes a 2 minus, magnesium makes a 2 plus, right? And so you end up with 4 minus as your product of the charges. And then magnesium and oxygen are both fairly small. O2 minus is large, but it's not as large, anywhere near as large as sulfate, which has 4 oxygens and a sulfur, right? So the distances are actually pretty small. So I'll just say that R squared is small. And that ends up being an insoluble compound. So this would have a stronger ionic interaction, or lattice energy, we'll call it. We're going to do a more careful and a more correct way to calculate lattice energy. This is a way to predict it. Magnesium oxide will have a stronger lattice energy than, say, sodium chloride. And so we're going to stop and do a short little quiz just to see if you're getting this. These are similar to problems you'll see on the website. So let's compare beryllium oxide to, let's make it lithium chloride. Let's look at the charges first. Beryllium is a 2 plus, oxygen is a 2 minus. So the product of the charges is equal to -4. The product of the charges here is 1 plus times 1 minus equals -1. So this is going to have much stronger Let's compare lithium nitrate. No, let's make it sulfate. Let's make it phosphate. So that would be Li3PO4. Now, phosphate is huge. It's a very large polyatomic ion. Phosphorus is big, and it's got those 4 oxygens. And again, you will learn how to draw these out and predict their shape. I'm drawing it flat. Really very large. And so the lithiums, the 3 of them, it's a 3 minus, isn't it? My bad. And so it's going to line up with the 3 lithiums. So the product of the charges, Q1 times Q2. Now, is that going to be 3 for Q1? There are 3 lithiums, but each of them is +1, and you're considering them one at a time, how it interacts with the minus. And so you have to think of it as 1 plus times 3 minus, or 3 minus. Consider instead Mg, magnesium phosphate. Let's look at the balance on this. Let's see if you can figure this out. I'm going to pause for just a second. What should be the formula? Well, you have a 3 minus and you have a 2 plus, so you're going to need 3 of these and 2 of these, adding up to an overall 6 for both of them, 6 plus and 6 minus. But when you're considering Coulomb's law, you just think of the magnesium as +2. So the product of the charges, well, let's take a look. What is going to be stronger, lithium phosphate or magnesium phosphate? Again, most important thing is to look at the charges. We already figured out this one's a -3. And then if we do this one, it's 2 plus times 3 minus, which is equal to a 6 minus, and that would be the stronger lattice energy. So picking up lattice energy has a very specific definition, and it is taking the ions X plus in the gaseous state plus Y minus also in the gaseous state going to X, Y solid. That's the energy involved of bringing these positive and negative ions from a figuratively infinite distance from each other where there's no real attraction. And then they come together and form the crystal in the lattice as we've drawn it before, right, where they all come together. You're going not from soluble like it's indicated here, but from gaseous ions down to the crystal lattice. So I want to know, let's consider it for sodium chloride. And of course, this could be a 2 plus or a 2 minus. You understand that. So if I'm looking at Na plus in the gaseous state plus Cl minus also in the gaseous state, and it's going to drop down to NaCl in the solid state. What is this energy? This is defined as the lattice energy. And you remember from Hess's law, you can follow any route you want to get to measure out all the individual steps and figure out what the missing bit is. So let's look at it like this. If you're going to start with Na, we'll have to make, let's say, an Na plus 1/2 of a Cl2. And eventually I want to get down to making sodium chloride in the solid. Well, I'm going to have to somehow get this to gaseous sodium plus. Think about the steps. I'm going to need to remove an electron from it to make it sodium plus. Oh, that's the first ionization energy. I'm going to need to make it a gas. Well, I can calculate how much energy I have to put in to convert sodium solid into sodium gas. Cl, I'm going to have to break it into Cl individual atoms, not Cl2. So I'm going to have to break that bond. And I'm going to have it pick up an electron. Oh, that's the electron affinity. So we have data for each of these things. So let's look at the steps we might go through. So let's say first thing we're going to do is we're going to make this Na gas plus 1/2 Cl2 gas. And that's the energy of sublimation. Sometimes you'll take it through two steps, to liquid and then to gas. And obviously that's going to be a positive. That's obviously a positive. I'm going to have to heat that up. Okay, and then I'm going to need to break the Cl2 into two individual Cls. So now I have Na and I have Cl 1 mole. We had a half of Cl2. I now have a mole of Cl. Well, that's the Cl2 So if I knew the bond energy, I'd know how much energy I'd have to put into that. And yes, obviously it's uphill. Okay, so now I need to take that to Na plus an electron. I'm going to remove the electron. And I'm still going to have my Cl atoms. And that, of course, is the first ionization energy of Na. So I can get that from the table. I have those data. So now I've got Na plus, a free electron, and a free chlorine atom. And now I'm going to take it right down here to Na plus and Cl minus by making that electron go onto the Cl minus. And of course, that is is the electron affinity of Cl, right? Going from a neutral atom, picking up an electron to make it the atom minus. And so if I don't know each of the individual steps, but I know if I don't know, say, this step, but I know all of these individual steps, like if I measure this one, this is just the formation of the enthalpy of formation of NaCl. So I know each of these steps, and I can follow, well, from here I have to add the energy of sublimation. I have to add the energy to break apart the bond energy between Cl2, and then I have to add the first ionization energy. And then it starts being negative, so I'm adding a negative electron affinity. I also know this was a negative, right? So that's going downhill. And if I know what each of these are, I can just add them all up, and I end up with what this difference is. We'll do a few of these. I'm not going to put a quiz of one of these on here, but we'll do a couple of these soon. And I think that's a good place to stop. It's a lot to take in, but the key thing I want you to realize is that each of these individual steps are things you've seen before, and now we're just going to put them all together. And I think I'll stop there.